Hello, students. I will wait one more minute and then I will get started. Actually, you know what? I'm just going to get started right now. Um, so, let me review what we did last time. Um, last time, we learned about the Biot-Savart law, which says the following, that the magnetic field produced by a wire carrying electric current is mu naught I over 4 pi times the integral around the loop of wire of dl cross r hat over r squared. And so I want to remind you, if this were a wire, for example, and let's say we wanted to calculate the magnetic field right here, okay, the wire is carrying current in a certain direction. So let's say we wanted to figure out what is the contribution to the magnetic field from that little piece of the wire. Well, dl points tangent to the wire, so there's dl. R hat points from that segment of wire to where we're calculating the magnetic field. And then the distance between that that segment of wire and the point P is what we call little r. All right. Mu naught is a constant of nature called the permeability of free space, and its value is 4 pi times 10 to the minus 7 Tesla meters per amp. Okay. So there you have it. We applied this law to a circle, and what we found is that if you have a current flowing in the counterclockwise sense around a circle, okay, and the circle has a radius r, then the magnetic field has a magnitude of mu naught I over 2r. And in the case of a counterclockwise current loop, that magnetic field is going to point out of the page in the z hat direction. Okay. We also learned that if you have a length of wire that's going straight, okay, and we want to know the magnetic field at point P1 or P2. P1 is directly in front of the wire, P2 is directly behind the wire. The magnetic field so the magnetic field at P1 and P2 is going to be equal to 0. Okay, so there's no magnetic field directly in front of a wire or directly behind a wire. And that is because if the point is directly in front or directly behind, you have this dl cross r hat term becomes 0. Okay? So, the first thing I want to talk about today is a handy rule for, and I'll put handy in quotation marks, for determining the direction of the magnetic field. Okay? So the reason I put handy in quotation marks is because we are going to use what I like to call right-hand rule number 2. Okay? So what you do, okay, is so right-hand rule number 2 is this. You take your right hand and you point your thumb with the current. Okay? And then the way your fingers curl is the sense of the magnetic field. Okay? So what I could do, if I wanted to more easily see without doing the cross product that the magnetic field is going to point out of the page for here, what I could do is I could take my right thumb and I point it in the direction of the current, and you can see that my fingers are curling up towards the camera. So because my fingers are curling up towards the camera, that means that the magnetic field in this loop is going to point out of the page. Okay? And similarly, outside the loop, if I put my thumb in the direction of the current, you can see that my fingers are still circulating, and if I go to the other side of the wire, my fingers are curling down into the page. So outside of the loop, the magnetic field points down into the page. All right? And so if we were to do sort of a three-dimensional view, so let me draw what the magnetic field lines look like three-dimensionally for a loop of current. I've got to draw this carefully here. So now we got, let's see. Have some precise drawing that I have to do. Appreciate your patience. Okay. All right. So if you have a loop of current, so here's the loop of current, you can see that in the center of the loop, the magnetic field is pointing out of the page. And then you can see the magnetic field lines go up, and then they curl, and then they point down. Okay? Right here. So that if we looked at the loop, sort of, if we looked at a cross section here, what we would see is that In the loop, the magnetic field points out of the page, and then outside the loop, it has circled back and gone down into the page. Okay, and so that can be seen with right-hand rule number 2. Okay, let's apply right-hand rule number 2 to an infinite straight line of current. So how do the magnetic field lines look for an infinite straight line of current? Well, we can think about this from a lot of different perspectives, okay? So I'm going to think about it from a side view. So from a side view, the infinite line of current looks like this. I'm going to think about what it would look like from a front view. And I'm drawing the current as a dot to indicate that the current is coming directly out of the page towards the camera. Or I could think about it from a 3D view. So, you know, it's kind of like, looks like this. Here's the line of current. It's going at like that. All right, so there's the current. So if we use right-hand rule number 2, from the side view, I put my right thumb in the direction of the current. You can see that my fingers are curling towards the camera, okay, above the wire. So the magnetic field is going to be pointing out of the page. So I'm representing that with dots. And actually, the closer you get to the wire, the more magnetic field lines there are, right? Because that's the way fields work. If you're close to the source of the field, then the field is stronger, okay? In that area. And then if I think about the lower side of the wire, the bottom half, my fingers are curling down into the page, down below the wire, okay? So it's the magnetic field curls around wires, okay? So the way that my fingers are curling is telling you the sense in which it's curling. So it's curling out of the page and then back into the page down below. Okay, so I'm putting X's to represent into the page. Like that, okay? Now, what if we were to look at this from a front view? So from a front view, my thumb goes in the direction of the current, which is out of the page, and I can see that my fingers are curling in the counterclockwise sense. So the magnetic field is going to make counterclockwise loops around the current. These are supposed to be circles, but I'm failing miserably at that. Concentric circles is what those were supposed to be. Okay, so the magnetic field is going around like that. If we were to think about this from a 3D perspective, here's the current. The magnetic field lines are looping around it. Okay. Draw some more. Like so. Like that. Okay, so the main idea is that the magnetic field lines loop around current carrying wires. So magnetic field lines have sort of a different character from electric field lines. If we remember, electric field lines, they start on positive charges and they end on negative charges. But magnetic field lines, they don't have a beginning or an end. They always make loops. Okay, so they're of a different character than electric field lines, which don't form loops. Now, what we think of as the north pole of a magnet is a place where the magnetic field lines are going out of. So this is like, so an electromagnet, for example, is simply a loop of wire that's carrying current. All right. So this, basically a circular loop of wire is an electromagnet. And so we can see that on one side of the electromagnet, the field lines are going out, and then the field lines circle around and they come back in here, like that. And so the point where the magnetic field lines are going in is what we call the south pole. So the north pole is where the magnetic field lines go out. The south pole is where the magnetic field lines go in. Okay? And compasses point tangent to magnetic field lines. Okay? So if you have a compass, let's say that's a compass, it's going to point tangent to the field line. So this is something that always confuses people, is if you're holding a magnet, like let's say that this is representing a bar magnet, the compass isn't going to point directly towards the North Pole. It's going to point tangent to the magnetic field line. Okay? So, I mean, this compass, if you think about it, it's pointing off in this direction, but the North Pole of the magnet is right here. So it points along the magnetic field line. But if you get the compass close enough to the magnet, then it's going to start to point towards the North Pole. Okay. Something like an infinite straight line of current doesn't even have a North Pole or a South Pole, because if you think about it, there's no location where the magnetic field lines are emerging from. They're just doing loops. So the idea of magnets having North and South Pole is really only for certain configurations of current. Okay. So what we're going to do now is we are going to using the Biot-Savart law. Okay. Little bug right here. Using the Biot-Savart law to calculate the current, or the magnetic field, excuse me, due to an infinite current carrying wire. Okay. So let's suppose that we have an infinite current carrying wire. All right. And so here's the origin. the wire is carrying current in the rightward direction, and it just goes on and on. So it goes to plus infinity, and it goes that way to minus infinity. So we're going to have an improper integral in the house. All right, and we want to calculate the magnetic field right here at the point P. And let's say that the point P is a distance, big R, from above the origin. Okay? So let's go ahead and single out a little piece of this wire, all right, at coordinate x. All right. So if we look at this, the dl vector is going to be tangent to the wire, so the dl vector is pointing in that direction. So clearly the dl vector points in the I hat direction. So this part's pretty easy. dl, all right, is equal to magnitude of dl, which remember is just dl without the arrow over the top, times I hat. Sweet. If we look at the r hat vector, it's going to point in this direction because it points from the current to the point where we're calculating the magnetic field. All right. So if I figure out what is the direction of dl cross r hat, the direction of dl cross r hat, well, I would put my pointer finger, so I'm going to rotate the paper to make this more comfortable for me. My right pointer finger in the direction of the first vector, which is dl. My right middle finger in the direction of r hat, which is that way. You can see that my thumb is going out of the page. So the direction of dl cross r hat at that location is in the z hat direction, out of the page. Notice that that is consistent with right-hand rule number 2 that I was talking about. Okay? Look, we saw that the magnetic field points out of the page if we have an infinite line of current that's carrying current to the right. So that's consistent. Now we need to get the magnitude of dl cross r hat. And so that's going to equal just to write that more formally, that's going to be the magnitude of dl vector times the magnitude of r hat vector times the sine of the angle between them. All right. The magnitude of dl vector is just dl with a without the arrow over the top. The magnitude of r hat is just 1 because it's a unit vector. And then sine theta is going to be the vertical component of this triangle. Okay? So I can see that, or it's going to be, the sine of this angle. So if this angle is theta, so I want the sine of that angle, but it's actually the same thing as the sine of this angle. So that's going to be opposite over hypotenuse. So opposite is going to be r. Hypotenuse is going to be, this distance is x, so it's going to be square root of r squared plus x squared. okay? And actually, since dl is pointing in the x direction, I'm going to write the magnitude of dl as just dx, okay? So what that means is that dl cross r hat is equal to its magnitude, which is this, times its direction, which is the z hat direction. All right? So that's that part. Then we have little r squared, which is the distance from this little segment of wire to the point P. And again, that comes from the Pythagorean theorem. So we have it's just equal to r squared plus x squared. So now we know what these things are, so we can plug it directly into the Biot-Savart law. So the Biot-Savart law is mu naught I over 4 pi times the integral of dl cross r hat, which is dx times r times z hat over square root of r squared plus x squared times 1 over r squared. All right? So that is the Biot-Savart law. So this term right here is dl cross r hat. This term right here is 1 over little r squared. And you can see that matches with the Biot-Savart law right here. Okay, so x is our integration variable, so we can factor out anything that doesn't depend on x. So in particular, I'm going to factor out r, and I'm going to factor out z hat. So mu naught I r over 4 pi times z hat times the integral of dx. And then when I combine these two terms, I have this is to the 1 power, this is to the 1/2 power, so I have the 3/2 power. And x runs from minus infinity to plus infinity. So I have to do this integral. All right. And so for completeness, I'm going to do that integral. And so you would do the trig substitution to solve this integral. So I would say x equals r tangent of theta. So what that means is that r squared plus x squared is to the 3/2 is going to be r squared plus r squared tangent squared of theta to the 3/2, which is r cubed secant cubed of theta. All right. So I'm using the fact that 1 plus tangent squared is secant squared, and then anything squared to the 3/2 becomes to the 3rd power. Okay. And then furthermore, dx is going to be r secant squared of theta d theta. And then our limits of integration, theta goes from minus pi over 2 to plus pi over 2. Why? Because as x goes to plus infinity, tangent of theta goes to plus pi over 2. And as x goes to minus infinity, theta goes to minus pi over 2. So this is trig substitution. If you don't understand that, don't worry about it. Just plug it into your calculator. All right. Mu naught I r z hat over 4 pi. And then this integral became the integral from minus pi over 2 to plus pi over 2 of r secant squared of theta d theta over r cubed secant cubed of theta. All right. And so canceling out, we have these two factors of r, and then we have three factors of r on the denominator. So we end up with one factor of r on the denominator. And then we also have these two factors of secant cancel out two of the factors in secant cubed. So we get mu naught I z hat over 4 pi r times the integral from minus pi over 2 to pi over 2 of 1 over secant, which is just cosine. All right? And so the value of this integral is just 2. So we get mu naught I over 2 pi r times z hat is the magnetic field. So this is a pretty important equation. It's the magnetic field from an infinite wire. All right? And basically what it says is that the further you are away from the wire, we're increasing the denominator. The further you are away from the wire, the weaker the magnetic field gets. Okay? And so that is exactly what I drew here, because you can see that I drew the magnetic field lines really close together if you're close to the wire, and then as you get further away, they get progressively further spaced out. Okay? Lower density of magnetic field lines further away from the wire. So that's how that works. All right? So this is a really useful equation. Now, like, what if I asked you something where, I don't know, I was like, what is the magnetic field you know, I have two wires carrying current out of the page. Okay? And I want to know, what is the magnetic field right here at point P? And let's say that this distance is say that this distance is x1 and this distance is x2. So let's think about, what is the direction of the magnetic field that each wire creates at the point P. So if I use the right-hand rule, I'm going to rotate my page. So I1, current 1, is carrying current out of the page. So I put my thumb out of the page, and I can see that at the point P, my fingers are curling in the counterclockwise sense. So wire 1 is creating a magnetic field that points in that direction. So that's the magnetic field from wire 1. Okay? Wire 2, I put my thumb out of the page, and you can see for wire 2, at the point P, it creates a magnetic field that's going down. So this is B2. So one wire is creating an upward magnetic field, the other one is creating a downward magnetic field. So if I wanted to know what is the total magnetic field at that point P, it would be mu naught I1, over 2 pi x1, because the point P is a distance x1 from that wire. And that one points upward, so I'll put a plus there. The second wire creates a magnetic field that points downward. So I'll put a minus in front of that one. And then the second wire is a distance x2 from the point P. So I have over 2 pi x2. And then the total result is going to be in the j direction because it's vertical. All right. Last thing I wanted to talk about today is there is a force between wires. Okay, so again, let's suppose that I have two wires carrying current. One is I1, one is I2. And let's suppose that these wires are separated by a distance r. Okay, so I1 creates a magnetic field. I1 creates a B that I2 feels. All right. In particular, again, using that right-hand rule, I put my thumb in the direction of the current, and I can see that I1 is creating a magnetic field that points upward at that location. Okay, so this is the direction of the magnetic field created by it. All right? And so if I wanted to find the magnitude of the force on wire 2, the magnitude, so I'll drop the arrow, it's going to be ILB sine theta. All right? Now, wire 2 carries an amount of current, I2. It has a length, which we'll call L. The magnetic field that wire 2 experiences is the magnetic field generated by wire 1. And we know that that magnetic field is given by this expression. So the magnetic field it experiences is mu naught I1 over 2 pi r. Okay? And then sine of theta. Well, theta is the angle between the magnetic field and the direction of the current flow, which is 90 degrees. So what we get is that the force between parallel wires is mu naught I1, I2, L over 2 pi r. This is the force between parallel wires. And it depends on the length. If you work out the direction of the force, you will find that parallel currents attract, and you will find that anti-parallel currents repel. Okay? At any rate, that is my lesson for today. And so I will see you in the Zoom room.